Welcome to BADM A724 Quantitative Methods and Business Analytics. This is lecture 11. I'm your instructor, Dr. Frank Tian Xie. In this lecture, we're going to cover correlation and regression, including correlation analysis, regression terminology, ordinary least squares method, test for significance, confidence and prediction intervals for y, unusual observations, and other regression issues. Okay. First, let's kind of like a refresh our memory about the visual displays of data, correlation analysis and visual displays. In visual display, let's begin with the analysis of bivariate data. That is, there are two variables with a scatter plot. A scatter plot displays each observed data pair x and y as a dot on an xy grid. It indicates visually the strength of the relationship between the two variables. We have talked about this before. And in correlation analysis, we use a correlation coefficient, or R, right? And the sample correlation coefficient R measures the degree of linearity in the relationship between x and y. And by definition, R is between +1 and -1. And when R is 0 equals 0, it indicates no linear relationship, or maybe some other curvilinear other relationship. Okay? This is how R is calculated. And the sum of the products, this is xi minus x bar and yi minus y bar, xi minus x bar squared summed and square rooted, and yi minus y bar squared summed and square root of that. So this is how R is calculated. This is correlation. Okay. And we can rewrite this as the xi minus x bar squared, this part here, as sum of square xx. We can rewrite this part, yi minus y bar squared, under the radical sign, as SSYY, sum of square y. And this part here, we can rewrite that as sum of square xy. Okay? If you do that, then the correlation coefficient R is simply SS sum of square xy divided by the product of sum of square x, the root of that, and the root of sum of square y. Okay? It's just a different expression. Right? And we have talked about this before. In a situation like this, when xy, the dot, the plot forms a straight line going upwards like this, we call that a strong positive correlation. And in a strong positive correlation, the R should approach +1. In this case, 0.9, plus 0.9. Okay? In the case of a strong negative correlation, the line goes down. As x increases, y decreases, and R approaches -1. In this case, -0.9. Okay? In the situation like this, we call this a weak positive correlation. There seems to be an upward positive trend here, but the correlation is not that strong. Not as strong as this one, but so we call that weak positive correlation. R in this case should be around 0.5, plus 0.5. In the situation of weak negative correlation, R is somewhere around the -0.5. Okay? When R is 0, that's when that indicates there is no correlation between x and y. Pretty much, they're not related as much. And be careful, when you see in a situation like a nonlinear relation like this one, it goes up like that and goes down. R could also be 0. So just be careful. Okay. How do we test for that? How we test for the R, right? And if we want to test for if to see if rho is 0, we use that to test for R is, remember, R is an estimate of the population correlation coefficient rho. There's a Greek letter rho, right? For the population, we want to test to see if R is 0, if R is significant or not, or if there's a correlation in the population. This is how we should do it. We start with the state hypothesis, determine whether you're using a one-tailed or two-tailed test, and level of significance alpha. Rho is 0 or not 0. 0 for H1, HO, and not equal 0 for H1. Then we can specify the decision rule. For degree of freedom n-2, you can look up the critical value in appendix D of your table. Then you can calculate. Okay. You calculate test statistic using this equation. Is a t-test r n-2 1 minus r squared. Right? You calculate t, and then compare your calculated t-test statistic with the critical value. Then you can make a decision. If the sample correlation coefficient R exceeds the critical value of R at alpha, then we reject null. If not, we cannot reject null. This is how you would test it. Okay? If using t-statistic method, we reject null t if t is larger than t alpha, or if the p-value is less than alpha, just like we did before. Normally the alpha is 0.05. Therefore, if the p-value is less than 0.05, we reject the null. Okay? And there's a quick rule for significance. There's a quick test for significance of correlation at at alpha 0.05. We use the absolute value of R to see if it's larger than 2 over the square root of n. Right? For example, if sample size is 25, n is 25, right? The quick rule will say if R is larger than that, 2 over the square root of n, or square root of 25, and then it's significant, right? And 2 over the square root of 25, 25 is square root of 25, of course it's 5, 2 over 5 is 0.4. That's a quick R, the quick rule R's critical value. And the actual R critical value is 3.396. You can see it's quick, is quite close to 0.4. If when n is 50, right, the quick rule is R should be, the absolute value of R should be larger than 2 over the square root of 50. And that square root of 50, we can calculate that. 2 over that gives you 0.283. The actual number is 0.279, quite close. In the case of R100, n is 100, sample size 100, the quick rule R is 0.2, actual 0.197. 200, quick rule is 0.141 versus actual value of 1.139. So it's quite close. We can just use quick rule to test for that. Okay. Now let's talk about regression. Regression. What is regression? What's the simple regression that we talk about? Right? Basically, simple regression analyzes the relationship between two variables. Correlation is also on that, right? But in this case, in regression, it analyzes the relationship between two, and it specifies one as dependent variable and the other one as independent variable. The dependent variable is also called the response variable, and the independent variable is called the predictor variable. Why? It's because, for example, if you want to find the relationship between income, lifelong earning income, and education, right? We normally would, from theory or common sense, we can argue that lifelong earning income depends on education, right? In other words, an earning or income is a response variable, is a dependent variable. It depends on education. So, and education in this case is called independent variable or predictor variable because we can use education to predict the response variable income. Okay, so be careful with the terminology: dependent variable, response variable, independent variable, predictor variable. Okay, the hypothesized relationship here will be linear. In other words, they form a straight line, right, or close to a line. And that, of course, is the most simple form of a relationship. You we're not dealing with the more sophisticated, complicated forms of a relationship between two variables. And but this is foundation for that. You can learn that later on in either other courses or on your own. Okay. For a line to be there, to exist, there are two things, right? We all know that from your college, I mean your high school or college algebra class, that you have to have an intercept for a line, and you have to have a slope. Once the intercept and the slope are determined, the line is determined, is fixed, right? So for the models of regressions, we need to estimate or calculate the unknown parameters. Beta 0, we call that intercept, and beta 1, which is the slope. Beta 0 intercept, beta 1 slope. So we need to calculate these two to determine the line. Okay? The assumed model for a linear relationship is this: y, the dependent variable, equals beta 0, the intercept, plus the slope beta 1 times xi, which is the independent variable or predictor variable, plus an error term for all the observations. Right? The error term is not observable. It's assumed to be normally distributed with a mean of 0 and standard deviation of sigma. We're hoping that's the case, right? That's the assumed model of a linear relationship. And the fitted model is what we use to predict the expected value of y for a given value of x. We use a y hat for that. Sorry, the hat is kind of like a of hat, right? So y hat, the fitted model, the predicted value of y equals b0, that's the estimated intercept, and b1, that's the estimated slope, times xi, the predicted variable. I'm sure you have learned about this before, studied this before, right? This is the fitted coefficients, b0 and b1, corresponding to beta 0 and beta 1. Okay? The residue or the error, the residue is y hat, the predicted value, minus true value of y. Okay? Residues, we call them residues. Residues may be used to estimate the sigma, the standard deviation of the errors, when that is unknown. Okay? In ordinary least square method, right, how do we find the slope intercept? Ordinary least squares methods, or OLS, right, OLS, estimate the slope and the intercept of the regression line so that the residues are small, right? And the sum of the residues is 0. So remember, if you have a bunch of dots between x and y, a bunch of dots on scatter plots, there are many ways for you to draw the line. Yeah, to draw a line that represents the relationship, right? It's not it's not always possible that all the dots are exactly on the same line. So it's a cluster, but forming like a line, close to a line. But how do you find the line that exactly represents everything, all the dots, or the best, representing the dots the best? One method is called ordinary least squares method. Basically, in this method, we assume the sum of the residues is 0, and we try to minimize the residues. Right? And basically, we look at the distances from each dot to the line and add them up. When that is the minimized, it's minimal, that is the line that we want. That's why it's called ordinary least square method. In this case, the sum of the residue is 0. That is yi minus y hat is 0. That's good, right? And the sum of the squared residue is what we call SSE, sum of square error, right? Sum of square error is the yi individual dependent variable values minus the predicted values squared, add up, summed up from first one to the nth one. Or if you use the equation for y hat, which is b1 minus plus b1 xi, you can plug that in, you get this equation. That's the sum of square error, SSE. For the slope, b1, right? And for ordinary least square method estimation, the slope is b1 is this is how it's defined and calculated. Or we know this is simply sum of square xy, and this is sum of square xx. So b1 is simply sum of square xy over sum of square x. And once b1 is known, we can calculate b0. b0, or the intercept, simply y bar, the mean of y, minus b1 from here times x bar. So once you calculate b1 and b0, the line is fixed, determined. Then how do we know it's a good line? And the fits data very well. So how do we assess the fit? Okay, we want to explain the total variation in y around this means. This means the sum is called sum of square total, for total sum of squares. Sum of square total is yi minus y bar, yi hat, y bar, right? That's the total variation in y around this means. This is the variations squared and summed, right? How do we explain that? How do we analyze that? Right? The regression sum of square is the explained variation, because that's the part that can be explained using the regression, and that part is y hat, that's your predicted value, minus y bar, the average value, the mean, right? So we call that SSR, the regression sum of square, which is the explained portion of the variation in y. We call it SSR. That's y hat minus y bar. So this is SST, this is SSR, and we have SSE. What's the relationship between the three? The SSE here is error sum of square is the unexplained variation in y, right? yi minus y predicted value. So that is unexplained. That part is the error. If the fit is good, SSE will be relatively small compared to SST, right? If you have a perfect fit, then the SSE will be 0. Perfect fit meaning all the dots are on the line. Of course, that's only in ideal situation. In real world situation, we probably will not see that. Okay. The magnitude of SSE depends on n and on the units of the measurement. Okay. And here we want to introduce another parameter called coefficient of determination. Remember, this is not a correlation coefficient, which is a small r, lower case r. This is a coefficient of determination, or r square, capital R square. That is a measure of relative fit based on a comparison of SSR and SST. SSR is sum of square regression. SST is sum of square total. Basically, R squared is defined as 1 minus SSE over SST, or SSR over SST, the portion of SSR of total, or the sum of square regression over sum of square total. That's the measure of the relative fit based on the comparison of these two. Okay. And by definition, R squared can only be positive, and it can only take a value between 0 and 1. It could equal 0 and could equal 1. Right? And r squared is often expressed as a percentage, as a percent. And r squared equals 1 indicates a perfect fit. 0, you know, no, not perfect, no fit basically. Okay? And in bivariate regression, only in bivariate regression, r squared capital R and r squared lowercase r, they are the same. Only in bivariate regression. Okay? If you look at the definition of a correlation coefficient r, small r, you see that they are the same. Okay? Standard errors of regression. The standard errors as yx is an overall measure of model fit. Another measure of model fit is defined as SSE or n-2, the square root of that. If the fitted model's predictions are perfect, SSE will be 0. Then S will be 0. Right? That a small s indicates a better fit. If the standard error is smaller, the fit is better. And if you use that to construct confidence intervals. Okay? The magnitude of S depends on the units of measurement of Y and on the data magnitude. Okay? And what about the confidence intervals for slope and intercept? We calculate the slope and intercept as a point estimate. And what about the confidence intervals? Right? This is a standard error we just talked about. And this is standard error for the intercept. SB0. Okay, and all you have to do is just know that how to calculate it. That's fine. Okay, that's standard error for the slope, and this is standard error for the intercept. Okay, test for this confidence interval for the slope and intercept then can be calculated like this. This is confidence interval for the true slope. You know, beta 1 is a true slope, and the confidence interval for that will be B1, here B1, plus this term or minus this term as upper limit and lower limit. Okay. Same case with the intercept, B0, the estimated intercept, plus this term and minus this term is standard error. We can use Excel, Minitab, Megastat, or other technologies to compute these intervals and do hypothesis tests relating to their linear regression. Okay. How do you test for the significance? Hypothesis test here, if beta 1 is 0, then X cannot influence Y. Right? If beta 1 is 0, meaning the slope is 0, X does not have any impact on Y. And the regression model collapses to a constant B0 plus a random error. You know, this, if the beta 1 is 0, right, there's nothing here. Y1 will be simply these two right here, and then you know the Y is basically constant. And the hypotheses to be tested are whether the slope is 0 or not, and intercept is 0 or not. Right? This is test statistics, okay? And a t-test is used in this case, and the degree of freedom is n-2 for slope and intercept. And the t value can be obtained from appendix X or from Excel for a given alpha level. If t is larger than your calculated t statistics here is larger than t critical, then you reject null. Or if a p-value is less than alpha, we reject null. Remember, normally alpha is set at 0.05. Okay. Let's do the analysis of variance on the overall fit, decomposition of variance. Right? To explain the variation in the dependent variable around its mean, we use this formula. Right? Yi, this the value of the dependent variable minus its mean, right, can be rewritten as this: yi minus y hat, that's predicted y, plus y hat minus y bar, y at the average y. Right? You can see these two cancel each other, so this equation holds true. Right? This decomposition is the same for the sum of squares. And if you do the sum of square, you should apply the same. So sum square yi minus y hat squared summed should equal to this squared summed and this squared sum, right? That's the same decomposition. So basically, the decomposition of variances could be written as SST, sum of squared total, the total variation around the mean, equals SSE, unexplained or error variation, plus SSR, this variation explained by your regression model. So SST equals SSE plus SSR. Okay? And then we can use the F statistic test, just like we did in ANOVA for the overall fit. For bivariate regression, the F test statistic is MSR, mean square regression over mean square error. That's the degree of freedom of regression is 1. The degree of freedom of error is n minus 2. So it's n minus 2 times SSR over SSE. That's your calculate F statistic. Okay? And then you look at the table from for the F critical. You can see if you are calculate F is larger than the critical value of F, you can reject null. Right? Or if p value is less than alpha, you can reject null. Okay? So to see if there's an overall fit. Okay? You can also construct the interval estimate for y, right? Predict the interval for y. The regression line is estimate of the conditional mean of y. An interval estimate is used to show a range of likely values of the point estimate. The confidence interval for the conditional mean of y is this. Use the y hat, the predicted value, plus or minus the whole thing here. Okay, we're not getting into there, but you know everything. The Tn is the t value, the standard error, and we know everything here. Okay, that's how you construct the confidence interval for y. Okay, and interval estimate for y here. I'm gonna let you skip that. You can use a quick rule for confidence and prediction intervals. Instead of using the full scale, full equation. Quick confidence interval for y is simply t times s, some standard error over the square root of n. You can use that for interval estimate. Quick prediction interval for individual y is this. This is for mean y. This is for individual y. Okay. Violations of assumptions. There are three important assumptions in regression. Right? One is the errors are normally distributed. Right? The errors are normally distributed. And two, the errors have a constant variance. That is what we call the homostatic. Right? That's the error terms have constant variance. And also the errors are independent of each other. Yeah, that is they are non-autocorrelated. Okay, you have to meet these requirements, assumptions, in order for the model to work. The error is unobservable. The residue from the fitted regression gives clues about the violation of these assumptions. Okay. The non-normality of the error is a mild violation, since the regression parameter estimates B0 and B1 and their variance remain unbiased and consistent. Confidence interval for the parameters may be untrustworthy because normality assumption is used to justify using student t-distribution. So our large sample size would compensate. So if you have a large sample size, that mild violation could be compensated. But if you have outliers, that could pose serious problems. So be careful when you use that. Normal probability plot. Yeah, we can use in the case of violation of assumptions. you can try use a normal probability plot to see, test. You can the HO in this case is errors are normally distributed. H1's errors are not normally distributed. You can test for that, right? If H1 is true, HO is true, the residue probability plot should be linear. You can also use display a histogram for the residues. A histogram, this is a standardized residue. There's a normal score. You can use that to see. What do we do about non-normality? Okay, remember the outliers affects that, right? So if you see a non-normality situation, you can trim the outliers if they are clearly mistakes. Sometimes you can tell if it's outliers really maybe just an error, right? Or you can increase the sample size if possible, and then or you can try a logarithmic transformation for both x y. Then you probably can correct for this non-normality. Right? Heteroscedastic errors or non-constant variance. The ideal condition is if the error magnitude is constant, right? That is, errors are homoscedastic. But the heteroscedastic errors increase or decrease with y. In the most common form of heteroscedasticity, the variances of estimators are likely to be understated. So this is just So this results in overstated t-statistics and artificially narrow confidence intervals. Okay. To test for heteroscedasticity, sorry, you can plot the residues against y. Ideally, there's no pattern in the residues moving from left to right. If you see a pattern like this, hopefully there's no pattern there. If it is a fan out pattern like this, fan out pattern growing larger and larger from left to right, right? Or funnel in pattern from larger to smaller, and that is a common pattern indicating heteroscedasticity. Okay. What do we do about heteroscedasticity? You can transform both x and y, for example, by taking log values. Although it can widen the confidence interval for the coefficients, heteroscedasticity does not bias the estimates. About autocorrelation is a pattern of non-independent errors. If the errors are not independent, right? In a time series regression, each residue ET should be independent of its predecessors. Right? For autocorrelation errors, in first order autocorrelation, an ET error in this T is correlated with ET minus 1 with the previous period. The estimated variance of the ordinary least square estimators are biased, resulting in confidence intervals that are too narrow, overstating the model's fit. So run test for autocorrelation. In the run test, count the number of the residues sign reversals. That is, how often does the residue cross zero contact center line. If the pattern is random, the number of sign changes should be n over 2. Fewer than n over 2 would suggest positive autocorrelation. Okay? More than n over 2 would suggest a negative autocorrelation. Okay? For that, to test for autocorrelation and the hypothesis, you can use Durbin-Watson test. Okay? The added HO is errors are non-autocorrelated, and the H1 is errors are autocorrelated. Okay? The Durbin-Watson test statistic is this, and the statistic will range from 0 to 4. If it's less than 2, it suggests a positive autocorrelation. Equals to no autocorrelation. That's the ideal case. If larger than 2, it's a negative autocorrelation. Okay. What do you do with that to do about autocorrelation? You can transform both variables using the method of first differences in which both variables are redefined as changes. You can do that. This is changes in x from period t1 to period t, and changes in y from period t minus 1 to period t. Although it can widen the confidence interval for the coefficients, autocorrelation does not bias the estimate. Okay? Unusual observations. We can use Excel, Minitab, Maxstat, and other technologies to compute standardized residues. Right? If the absolute value of any standard residues is at least 2, then it's classified as unusual values. A high leverage statistic indicates the observation is far from the mean of x. These observations are influential because they are at the end of the leverage, so it has a leverage. Okay? The leverage for observation I is denoted as hi. Okay? For this part, hi, a leverage that exceeds 3.301n is unusual. Right? You can use studentized deleted residues. They are another way to identify unusual observations. A studentized deleted residue whose absolute value is 2 or more may be considered unusual. A studentized deleted residue whose absolute value is 2 or more is an outlier. You can use that to determine outliers. There are other regression problems. Okay, one is outliers. Right, the outliers may be caused by first, an error in recording data. That's bad. If you record data, there's an error that could cause an outlier to take place, and or from impossible data, okay? Or an observation that has been influenced by an unspecified lurking variable that should have been controlled but it wasn't controlled, okay? And that could result in an error, right? To fix the problem of outliers, you may have to delete the observations, or you delete the data, or formulate a multiple regression model that includes the lurking variable we talked about. There's another variable that was not considered. Okay. Also, the model misspecification could be a problem. If a relevant predictor has been omitted, then the model is misspecified. Okay, you forgot something. You forgot to include something important, an important predictor variable. You probably can use the multiple regression instead of bivariate regression in this case to solve for that problem. Or it could be yield conditioned data. Well conditioned data values are of the same general order of magnitude. Yield conditioned data have unusually large or small data values and can cause loss of regression accuracy or awkward estimates. Okay. For yield conditioned data, avoid mixing magnitudes by adjusting the magnitude of your data before you run your regression. Yeah. Spurious correlation. In a spurious correlation, two variables appear related because of the way they are defined. But the problem is called the size effect, or problem of totals. Model form and variable transforms. Sometimes a nonlinear model is the better fit than a linear model. Right? Not everything is on the line. Right? Excel offers many model forms that you can choose from, you can explore. Variables may be transformed, either use logarithmic or exponential functions in order to provide a better fit. Log transformation reduce heteroscedasticity. Yeah. Nonlinear models may be difficult to interpret, so it's not that easy.